Let's look at a spring problem and then solve it two different ways, as a one-object system and then as a two-object system. Check out this 2-kilogram box that's squeezed up next to a spring attached to a wall. What's a question that you might ask? A typical question might be, how fast is the mass moving after the spring launches it to the right? Check out this animation. Boing. Let's bring the mass back, and to solve this problem, we're going to use the original work energy theorem for a one mass system. We're only going to be zooming in and looking at the 2-kilogram object. That's going to be our system. And if it's a one object system, the original work energy theorem states that the initial kinetic energy plus the total amount of work done by all of the forces acting on the object is equal to the final kinetic energy. In this case, what are there? Three forces acting on that object. You have the weight force pulling it down. You have a normal force pushing up on the bottom. And then you have this spring pushing it to the right. Well, the only one of those three forces that's going to be doing any work is this spring force right here. The normal force and the weight force are both perpendicular to the direction that the object's going to be going. So those two forces don't do any work. So this work total is just going to be the work done by the spring. And we know how to calculate work. It's the force multiplied by the forward displacement multiplied by the cosine of the angle between the direction of the force and the direction of the forward motion. But is this a constant force? If it's not, we would have to use the average force to figure out the work. Let's think about that force that the spring puts on the mass during the launch and answer these questions as we go forward. Number one, what is the initial force on the mass? And number two, does this force remain constant as the spring returns to its normal uncompressed length? Watch the animation again and then sketch the force versus elongation graph showing the force acting on that 2-kilogram box. Here we go. So, what'd you get for the original force? We know that the spring constant is 4 newtons per meter, and Hooke's law tells us that the force acting on this object due to the spring is equal to negative kx, and in this case, the spring constant is 4 newtons per meter, and the elongation is negative 6 meters since it was compressed. And if we calculate that out, we get 24 newtons. So when the spring is compressed all the way here, the full 6 meters, this spring is going to be pushing against that object with a force of 24 newtons. But does it stay 24 newtons? No, because as the box takes off, the elongation from the equilibrium position decreases, and therefore so does the force. Let's take a look at the animation and the force versus elongation graph as it's drawn. Here we go. Is this what you drew? Notice the force linearly went from 24 newtons down to 0. And then, of course, it stayed 0 because the spring wasn't pushing on it anymore. Now, if we wanted to calculate the work done by this spring force, we could use the average force of 12 newtons. However, there's another way of getting the work done, and that is to simply find the area underneath the curve. If it's above the x-axis, it's considered a positive area. If it's below the x-axis, it's considered a negative area. So in this case, this area would be 1/2 base times height because it's a triangle. And the base would be 6 meters and the height would be 24 newtons. So the work done would equal 1/2 times 6, which is 3, times 24, 72 Newton meters, or 72 joules. So that's how much work the spring force does on that 4-kilogram object. So now we can go back and calculate how fast that object is going. The initial kinetic energy plus the work done by the spring force equals the final kinetic energy. But we know that object started from rest, so there isn't any initial kinetic energy. And we just calculated that the spring force did 72 joules of work on that object. And the kinetic energy formula is 1/2 times the mass times the final velocity squared. So we'll have 72 joules equals 1/2 times 2 kilograms times the final velocity squared. And if you solve that for the final velocity, you get 8.5 meters per second.